All right, number 7 here says, which is more highly regioselective, the addition of HCl to methylene cyclohexane or 1-methyl-cyclohexane? All right, all they mean by the regioselective is I want you to remember that this is going to go on potentially two different ways. So if I actually just draw a basic alkene with just two carbons, and what I'm going to do to distinguish it, I'll do an R and an R prime, and then an R double prime and an R triple prime, just to draw attention to the fact that all three of these things could be different. All right, on addition of HCl, what would guide it to choose one or the other would be the number of H's off either side. But if I have R groups on both, all the way around on all those sides, I could do an H here or a Cl here, or vice versa. I have a lot of products possible. What makes it regioselective is if I happen to have a location with more hydrogens. All right, so let's look at methylene cyclohexane. So cyclohexane, methylene, has a double bond going just out like there. Now, this is two hydrogens on there, and then that ring on it. So if this one were to react with some HCl, we would totally expect a Martinov product and pretty much only one product, because the carbocation that is created, I'll leave those two hydrogens here. I would add a hydrogen there, most likely, because the hydrogens go to the side of more hydrogens, and a cation there. Well, the other option on that, to reverse those two, would have the hydrogen added here and the cation there. But this one is actually a primary carbocation. We know from our textbook those aren't very stable. We pretty much wouldn't see it at all, because we have tertiary here, primary here, and when there's that drastic of a difference, tertiary is pretty much the only thing seen. So it's actually so regioselective, we can guarantee one product. It's actually going to end up almost definitely putting a chlorine right there, and that's the only product we're going to get. All right, but if I go with methyl cyclohexane as our starting ingredient, so methyl cyclohexene, assuming those are both one since they're not mentioned, the cyclohexene part must be at 1. So to actually look like something like this. Well, when I mix that with HCl, I definitely could make the exact same product, where I protonate this side, or add a hydrogen there, and then add a chlorine to the other. And that would be the major product. We get the same thing. But at least on this one, I would get a considerable amount, or a detectable amount, of the minor product, where the chlorine is here, because that's just where we put the hydrogen on this side, the anti-Markovnikov product. But the beauty of this one, and how we could see it, is this would actually create a carbocation. All right, so as fast as that was, what I want you to focus on both of these is what guides either one of these to be regioselective is simply how the first hydrogen goes on there. So I'm going to leave I'll put the Cl here. I want you to focus on the fact that the double bond attacks, always. It always gives us two possible carbocations based on where that double bond is. We're either going to put a hydrogen on the left or the right. We could either get that carbocation, I don't want a plus, I want an or we get this carbocation. Either side of where that double bond was. This one's tertiary, that one is primary. When there's that big of a difference, you're pretty much only going to make that one. But with our other one, the methyl cyclohexane, when we make our two carbocations, we're going to have that same one tertiary, but the other one made here puts that cation there, making it secondary. And since those are both are reasonably stable, we would get products based on those. So we'd have a major and a minor product from those two cations. Yet over here, we wouldn't get that at all. So most regioselective is definitely the methylene cyclohexane, because it gives you carbocations that either would be tertiary or primary, and you can pretty much disregard the primary.